So the Applied Mineralogy Group is a special interest group of the Mineralogical Society. And we run things like this. Normally we would hope to have more in-person conferences, but at the moment we've adapted and have moved online. So we have a whole range of kind of what we call open geoscience talks, trying to hit a nice range of things that we hope will be of interest to the community. I'd just like to bring your attention to two bursaries that we run. One is the Hazel Pre-Shard Student Bursary, and the deadline for that is the 15th of February. And our own student bursary, which is the deadline, is the 1st of March. And all that information can be found on the MinSoc bursary pages. We're really hoping that we have, obviously 2020, we didn't have much in the way of applications. So we do hope that we'll have more this year. Please, if you're interested in this, we will be sending out details of the next talk. Sending out details of the next talk. So we will send a message around after this if you'd like to know more information. We will add you to that mailing list. Please join us in the Mineralogical Society. We're very interesting, I hope, and we run a lot of things, and not just us, all the other special interest groups. And it is free for students for their first year. So please do encourage them to get involved if you think it's relevant. And the final thing is that the AMG actually produces a little bulletin called the Applied Mineralogist, which is kind of everyday applied mineralogy and lots of special features on a range of different topics. And that's all freely available on our website as well. And with that, I will hand over to Juerg, to Alicia, and I'll be quiet. Thanks very much.
Many thanks, Imar. That's great. So I would like to introduce our speaker today, who is Professor Juerg Matter. He's a professor of geoengineering and carbon management at the University of Southampton, UK, since spring 2013. Matter was previously an associate research professor at Lamont Doherty Earth Observatory and an adjunct assistant professor at the School of International and Public Affairs at Columbia University, New York. A key focus of his research is on developing novel methods for removing carbon dioxide from the atmosphere to mitigate global warming. He is working on field trials for CO2 removal by direct air capture and by enhanced rock weathering and mineral carbonation. In addition, he's developing methodologies for monitoring and verifying CO2 storage and potential leakage from storage reservoirs. Matter has made fundamental advances in understanding permanent carbon storage in unconventional geologic reservoirs, such as basaltic rocks and mantle peridotites. He received his MSc and PhD from ETH Zurich in Switzerland. And with that, I would like to welcome Juerg, and Juerg, the floor is yours. Thank you.
Excellent. I hope everyone can hear me, correct?
Yes.
Good, excellent. So thank you very much, to the Mineralogical Society to invite me to give this presentation. The plan was to really talk about permanent and rapid greenhouse gas removal via carbon dioxide mineralization, but I was also asked to talk a little bit about the CarbFix project, which I was part of in the initial stage of the CarbFix project, which obviously evolved much further now, and you will see that at the end of my presentation. So, but before I start, I would like to give some perspective why we are thinking about carbon storage, actually. And, if we look at sustainable development, and if we look at how much we, as human beings consume and consume basically resources from Earth, you can see on this slide here, is an example of every American born will need, and you can read that yourself, but basically every American born will need 1.2 million pounds of minerals, metals, fuels in their lifetime. And, that's quite similar here in Europe too. So the question really comes up then on the planetary boundaries, do we reach the boundaries of Earth? Can Earth provide, all these metals, resources and fuels we need? And certainly, in terms of growing population, this is a really good question. But something else is produced by this basically consumption of Earth resources, and that's environmental stress. And today, I will focus on one particular environmental stress, and that's, the disposal of greenhouse gas emissions into the atmosphere, and actually how we can mitigate that environmental stress. And as you know, the anthropogenic perturbation of the global carbon cycle is quite enormous. We use the atmosphere as basically a disposal, disposal site for our greenhouse gas emissions. And on this slide, you can see basically that perturbation illustrated in the red arrows. And, through fossil fuel and industry, greenhouse gas emissions from fossil fuels industry, which are, around, 34 billion tons of CO2 per year, they are emitted into the atmosphere. 17 of that stays in the atmosphere for quite a long time. And then, roughly 5 gigatons are emitted from land use change. And obviously there are also sinks, and there is, the ocean is a big sink, as you can see here, with roughly 9 gigatons of CO2 per year. And the biosphere is also a huge sink. But, important, a lot of that greenhouse gas emissions and namely, carbon dioxide stays in the atmosphere. Okay, let's move forward. So, that disposal of greenhouse gas emissions into the atmosphere, as we all know, produces global warming. And if we look at this graph over, the last a few decades, the warming, we basically warmed the surface of the Earth around 1 degree Celsius. Correctly, the newest numbers are 1.2 degrees Celsius. So that's the global warming. That global warming is basically the result of our anthropogenic perturbation of the carbon cycle. And, where we are heading, that's a big question. And here, on this part of the graph, you can see different model calculations. And, but right now we are still on this business as usual scenario, and we would reach, by 2040, the 1.5 degrees Celsius. Basically, we would reach the limit that was discussed in the Paris Agreement. So what is the task? What is our task? What do we have to do? What we have to do is basically illustrated on this graph. We have emissions from fossil fuels and land use change in gigatons of CO2 per year as a function of time from the 1980s to the 2100. And we are right now here, in 2020. And what you can see in all these different colored lines here are projections from socioeconomic pathways calculated, and published in these ICCP reports. But what you can see, if we really want to limit global warming below 2 degrees Celsius, which would be roughly, a 2.6 watt per square meter warming, we will be on this blue line here. And you can see that, soon we have to, we request negative emissions. But, it's clear by this graph that we have to mitigate this global emissions from fossil fuel and land use change. So just to recap that issue is, we have sources of carbon dioxide and we have sinks on the other side. Sources, 88% are from fossil burning and industrial activity, and roughly 12% are from land use change. That includes, deforestation. And then the sinks, we have the atmosphere, 47% of that annual CO2 emission stays in the atmosphere, 30% are absorbed by the biosphere, and 24% are absorbed by the global surface oceans. There's an imbalance, and it's not quite clear where these 2 gigatons of CO2 per year are going right now. But so what are our response options and for this mitigation? So I will not obviously talk about all of these response options, but we have 2 categories. One is, we can reduce emissions, or, we can reduce carbon sinks. And today I will talk about a specific example of, reducing emissions by carbon capture and storage, but by kind of an unconventional carbon capture and storage method that we tested in the CarbFix project. So what is carbon dioxide capture and storage? It's basically a chain of different technologies. CO2 is captured at its source. That can be power plants, cement factories, that can be petrochemical industry, other industry, ammonium plants, but we can also capture CO2 directly out of the atmosphere. And then that CO2 has to be transported to a storage site, and it has to be injected or stored at a storage site. What we as geologists think about a lot is storing CO2 in geologic reservoirs in the geologic subsurface. But at that point, the job is not done. We obviously have to monitor and account basically the stored CO2 to make sure that none of that CO2 is leaking back to the surface, which is obviously a critical part of this technology change. So, oil industry is injecting CO2 for many decades now for enhanced oil recovery. And we learned a lot from that, and we learned a lot from oil industry. And generally, CO2 is injected for storage below 800 meters depth, where, there is a phase change because of pressure and temperature change. The CO2 changes from a gaseous phase to a so-called supercritical phase. But important to realize is that this supercritical CO2 is still less dense than the reservoir fluids in that reservoir, and because of this density difference between the supercritical CO2 and the reservoir fluids, there is a buoyancy force, and CO2 basically moves upwards through the reservoir until it hits a permeability barrier. So generally in a geologic reservoir, we need a permeability barrier. We need a low permeability cap rock, an impermeable cap rock, in order to keep that CO2 down in the reservoir. Obviously, while we store that CO2 over time, there will be changes to that CO2. So over time, CO2 will dissolve in the reservoir fluids, and over time it will react with the reservoir rocks. So obviously, there will be a change, but that buoyancy force is a critical part, if we think about safety or the safety of CO2 storage in geologic reservoirs. But as we know, as geologists too, the geologic subsurface is not a leak-proof container. It is not like my container, my experimental autoclave in the laboratory, which is obviously leak tight. The Earth subsurface is not leak tight. There are fractures, there are cracks, there are abandoned boreholes, especially if we think about former oil and gas fields and former depleted oil and gas reservoirs. So there is a risk that CO2 leaks back to the surface. So many years ago, we started to think about, and we started research on thinking about how we could permanently store CO2 in the geologic reservoirs. And obviously nature shows us or demonstrates to us how we can do that. So nature, through the process of weathering of silicate rocks, basically converts carbon dioxide to carbonates, basically to limestone. So we are interested in terms of permanent storage to use silicate rocks, reactive silicate rocks, to basically convert that CO2 to carbonate minerals. So this process, requires silicate rocks that are rich in divalent cations like calcium and magnesium or iron. And as we know from nature, this process occurs. You can see here images, below here are carbonate terraces in the mantle peridotite of Oman. So there, CO2 is captured through a water-rock interaction with mantle rocks. Similar example here, all the white stuff is magnesium carbonate. The darker stuff is still mantle peridotite. And here you can see an example of a core we drilled in Iceland, where you can see here in this fractured calcite mineralization happening. So that is happening through fluid rock interaction with this calcium magnesium silicate rocks. And what we just want to do, we want to engineer that process, and we want for the purpose of carbon mitigation. So what's really required is for mineralizing that CO2 is that we combine that CO2 with divalent cations, and some very simple reactions, equations are shown here. So obviously ideal rocks, ideal silicate rocks are, rich in calcium, magnesium, ions. So it is, the mineral olivine or pyroxene that basically reacts with water and CO2 and precipitates calcite, simplified in this reaction. Another reaction is, that's a critical one in mantle peridotites, where you have serpentine and brucite. That brucite reacts with CO2 and forms a magnesium carbonate. Similar, in basaltic rocks, the basaltic rocks are rich in plagioclase, calcium plagioclase, reacts with CO2 and water, forms calcite and a clay mineral in this equation. So that's what we would like to engineer. And we have to engineer it because, the natural process of weathering is a slow process, and we have to speed that up. So far before, we started the CarbFix project, there was a lot of knowledge available from laboratory experiments, and that's shown on this graph here. These are reaction rates of, in black, basaltic glass, crystalline basalt, diopside, forsterite, chrysotile, and actinolite. This data was summarized, by Sandra Snansborgsdottir and published in Nature recently in a review paper. So we know reaction rates of these calcium magnesium silicate minerals. We know reaction rates because of laboratory experiments, where we tested, reaction rates on crushed materials or on single minerals. We also know from numerical simulation studies, which reservoirs have the potential for mineralizing CO2. And as illustrated here, and that is a work published by Harrison et al. In 2019 for, the Utsira sandstone, which is a major storage reservoir for CO2 in the North Sea, used by Statoil for CO2 storage. But you can see that the graph shows basically, the gas injected or the percentage of injected CO2 that stays as gas in the reservoir over time, and the part of the CO2 that gets dissolved in the reservoir fluids and the part that gets mineralized in the reservoir. So there's very little mineralization happening in that storage reservoir because the Utsira sandstone has basically very little, or the composition, is not rich in calcium, magnesium, silicate minerals. Compared, down here, an example from the Ordos Basin in China, it's different. That's also a sedimentary basin, but the sediments are rich in calcium, magnesium, silicate minerals, especially here chloride. And you can see that the percentage of CO2 that is getting mineralized and precipitated as carbonate minerals is increasing over time here. And you can see that it starts, after 10 years, and then, most of the CO2 will be mineralized after 1,000 to 10,000 years. So these are still, very slow mineralization rates. And before we started the CarbFix project, we were really interested to test that in the field in a pilot scale project on a certain scale. So what we did in CarbFix, in the CarbFix project, and here, I really talk about the pilot project that we did, basically in 2012. The project started officially in 2007. We then did all, the preparation and did an injection of 175 tons of CO2 between January and March 2012. That was followed by a combined injection of CO2 and H2S in 2012. And I will show results of both injections, but mainly we'll focus on that 175 tons of CO2, the pure, we call that the pure CO2 injection. So obviously, this project was quite big. It's a pilot scale project. It was the first injection into basaltic rock, so into, an unconventional storage reservoir at that time. And we joined effort, with the University of Iceland, led by Siggi Gislason. Reykjavik Energy was our industrial partner in Iceland. University Paul Sabatier in Toulouse with Eric Oakers was part of it, and the Icelandic Geosurvey, and us, at that time at Columbia University in New York. So our field site is basically captured in this image. Here you can see the Hengel volcano, and that's basically, where or deep down, under that past volcano, Reykjavik Energy is basically producing steam, geothermal steam. That steam is used to run turbines. At that time, this geothermal power plant was a 300 megawatt electricity power plant, and some hot water production for the city of Reykjavik. But, this power plant, geothermal power plant, is also our source of CO2, and it's the source of hydrogen sulfide. So, it's very common that geothermal power plants produce, a lot of other gases, and one of it is H2S. And so we basically, together with Reykjavik Energy, we developed an injection site down here, in southeast, or from the power plant, 3 kilometers away. We built a pipeline that basically piped the CO2 to that injection site, and the CO2, or at least later, was captured from the power plant before the steam was used in the turbines. So this is basically, the framework of our pilot study. As I mentioned before, the source of the CO2 is a magmatic source. It's the solidifying magma below, that mountain, or in the deep subsurface. And that's, also the source of the heat that basically fuels the geothermal system. But with, the geothermal steam, the power plant produces 40,000 tons of CO2 per year and 12,000 tons of H2S emissions per year. And all these emissions in the past were obviously emitted into the atmosphere. This is very little, compared to a 300 megawatt coal-fired power plant, but it was an ideal setting for us to test CO2 storage in basaltic rocks, because Iceland, the most dominant rock in Iceland is basalt, and we also had a CO2 source. Here you can see the setup, a schematic of the setup of our field site, which we developed. The power plant here. So we had a pipeline, a CO2 pipeline, transporting the CO2 to an injection well. So we used pre-existing infrastructure from Reykjavik Energy. So this injection well is a 2-kilometer deep vertical borehole drilled by Reykjavik Energy many years before we started the experiment. And then we had several other boreholes downstream in the same formation. And we use these boreholes as a monitoring borehole. So monitoring wells, so we could basically monitor what's happening with the CO2 after the injection. And as you can realize, our dominant storage reservoir for this pilot project was, consisting of olivine thoolite. It was basaltic flows. Above and below, our storage reservoir, which was a target storage reservoir, which was at a depth 400 to 800 meters, was, above was a hyaloclastite. These are glassy basaltic rocks, quite low permeability. So it forms kind of a cap rock, but we did not really rely on that because our injection occurred actually at 540 meters. And as you can remember, at 540 meters, the CO2 is still in a gaseous phase. So we don't have supercritical CO2 in the reservoir, we have gaseous CO2, and that's why we had to come up with a different injection scheme. So we had to come up with a different technology how we inject the CO2. So here you can see what we basically designed in that first phase of CarbFix. Traditionally or conventionally, CO2 is injected as a pure supercritical CO2 into a geologic formation. But because we were too shallow and we didn't really have a cap rock above or a reliable cap rock above, we basically co-injected with the CO2 water. So that water was pumped from a nearby borehole, was transported to the injection well and was co-injected together with the CO2 to 540 meters depth. So basically the CO2 in the borehole was sparged into that water stream that goes down into the borehole, injection borehole, and the CO2 sparge produced very tiny bubbles of CO2, and the water drags them deeper down, and obviously all the CO2 bubble dissolve. So what goes into the formation is basically sparkling water, or a seltzer water, but that water had a lot of CO2 dissolved in it, and the pH of the water was, roughly 3.5. So acidic water loaded with dissolved CO2 was injected into that basaltic reservoirs. So because we had a single phase fluid injected, obviously we cannot use geophysical monitoring techniques because we do not have that contrast in physical properties between, a supercritical CO2 and a formation fluid. So we had to come up and design a different monitoring, or we had to design a different monitoring plan. And so we used geochemical traces. So that's illustrated here. We used non-reactive traces like sulfur hexafluoride, SF6 or SF5CF3, and we used the dye tracer sodium fluorescein. And we also used the reactive tracer radiocarbon, and I will tell more about that in a minute. But so we had the dye tracer, and this radiocarbon was co-injected together with the water into the injection borehole. While, SF6 and SF5CF3, which are gases, obviously, they were co-injected with the CO2 into the borehole. So we added SF6, SF5CF3 to the CO2 gas, and, we added a dye tracer and the radiocarbon into the water stream. And here you can see our injection rates, they were for the CO2 0.07 kilograms per second, and we injected 2.0 kilograms per second of water. So both, were injected together with the traces. So why radiocarbon? At that time, we were really thinking about we need a reactive tracer, because what we really want to trace is the fate of the CO2 and the fate with regard, to mineralization. We were interested how fast does our CO2 get mineralized through reaction with the basaltic rocks, because we already dissolved the CO2 before it entered the formation. We already trapped the CO2 as dissolved CO2 in the injection fluid. So the big target we want to address was how fast are in situ mineralization rates for the injected CO2. And there is no more ideal tracer than the carbon itself, because we inject CO2. So what we did, we basically labeled the injected CO2 with radiocarbon. And that's kind of a common method in biogeochemical studies. So by tagging the injected CO2 with radiocarbon, we can distinguish it from any ambient carbon in that storage reservoir. Because the storage reservoir, the ambient carbon in the storage reservoir is more or less radiocarbon free. So there's no radiocarbon, its isotopic signature of the ambient carbon in the reservoir is, does not include radiocarbon C14. So we can quantitatively define CO2 brine rock reaction with this method. We can come up, with a mass balance of the injected CO2. And as you can see here, there are, the target C14 activity in the injected water was 12 becquerels per liter. And you can see here, that the C14 concentration was 5 times more than in the injection compared, to the 1850 background. But, because we have dilution happening in the reservoir between the injected fluid and the ambient fluid in the reservoir, basically the result was that the radiocarbon concentration in the water in the reservoir was not above than basically, the ambient in the atmosphere. So, in terms of environmental pollution, it was basically not an environmental pollution. And here you can see a schematic of the environmental setup. So what we did is basically a forced gradient test. For some of you being hydrogeologists, you're familiar, with the forced gradient test to test aquifers. But what we did, we injected a dissolved CO2 in the injection borehole. And then we had, 125 meters apart downstream from the injection borehole. We had our first monitoring borehole, HN04, and there we continuously pumped water out of that borehole. So what we did, we produced a gradient, a hydraulic gradient from the injection borehole to the monitoring borehole. And we drawn our injected fluid towards that first monitoring borehole. Further downstream, we had other monitoring boreholes. But the data I show is basically data from this monitoring borehole, the first one, downstream from the injection borehole. Here you can see quite a complicated graph, and it shows basically the concentration of our inert traces, so non-reactive traces in the reservoir, collect or measured in samples collected from that first monitoring borehole. So in blue, you can see the sulfur hexafluoride concentration as a function of time. And these gray bars show basically where, the different injection phases. So this was the pure CO2 injection, and this was the CO2 and H2S injection here. And let's just look and focus on these blue diamonds. And these blue diamonds are basically showing the SF6 concentration in the fluids pumped from the first monitoring borehole. And what I have to emphasize again, you know, SF6 is a non-reactive tracer. It is just, you know, basically dilutes as a function of the mixing, the dispersion happening in the underground reservoir. And what you can see here is a first breakthrough curve after breakthrough, you know, of the traces in the monitoring borehole at, you know, roughly 60 days after injection started. And then, you know, we have a large breakthrough, you know, the main breakthrough of that non-reactive traces occurred for roughly 400 days after the pure CO2 injection occurred. And that tells you that, you know, here, the bulk of our injected fluid basically passed that monitoring borehole. So after 400 days. Here you can see the same curve, you know, for the radiocarbon concentration of the dissolved inorganic carbon as a function of time. So this is the same. So we see, you know, that initial peak after 60 days, and then basically radiocarbon dropped and it stayed constant. Okay, so we do not see a main peak after 400 days. Which was already, you know, like, wow, okay, what is going on in the subsurface? Then here, we did not only measure, you know, the concentration of our traces, the reactive tracer, which is radiocarbon, and the inert non-reactive traces, SF6 and SF5CO3, but we also measured all, you know, the chemical composition of the fluid. And here, you know, you see in blue, the monitoring, the data of the pH in that monitoring borehole. Again, you know, it dropped to a minimum of 6.6, you know, 60 days after the injection started. This coincides with, you know, a peak in the dissolved inorganic carbon concentration here in red dots at the same time. Then pH recovered, and then, you know, more, you can see a little bit, you know, a decrease in pH after the second injection, but then more or less it stayed constant. And the same, you know, the dissolved inorganic carbon concentration stayed constant more or less. There is no big peak recognizable, you know, at 400 days, where, you know, our inert tracer SF6 shows that the bulk of our injected CO2 basically passed by the monitoring borehole. We don't see that in the dissolved inorganic carbon. So something happened to the carbon we injected. So with this tracer data, we can then basically calculate first, you know, the mixing between the ambient reservoir fluid and the injected solution, illustrated here with this equation. So we know for each water sample we collected, we know, you know, the amount of, or the percentage of the ambient reservoir fluid versus the percentage of injected fluid in that sample. We can then calculate, you know, a mass balance for the dissolved inorganic carbon, or for, you know, the radiocarbon, the reactive tracer, based, you know, based on pure mixing. So we can say, okay, if we have pure mixing, just mixing between the reservoir fluid and the injected solution happening, we would expect that much, you know, that concentration of radiocarbon or that concentration of dissolved inorganic carbon in the reservoir. And the difference, you know, between the expected concentration, the actual one we measured in the retrieved fluid samples, that, you know, basically tells us how much carbon reacted with the rock. So here you can see basically that mass balance. So I showed the dissolved inorganic carbon in moles per liter as a function of time. We have these initial peaks here, and, you know, we have no peaks at 400 days. So in gray, you can see the dissolved inorganic carbon we measured in the reservoir fluids. We monitored that in the reservoir fluids. And in red, you can see the expected concentration if we just have pure mixing happening in the reservoir. And there is a huge difference. And that difference is we lost carbon, dissolved carbon, on its way, you know, to that monitoring borehole. So we that loss, obviously indicates that 95% of the injected CO2 reacted, and 95% of the injected CO2 was basically carbonated through water-rock interaction with basaltic rocks and was permanently stored. So for the first time, in a pilot scale project, we could demonstrate that these reactions are really fast in a reservoir, and these reactions lead to permanent storage of CO2 in form of carbonate minerals in a reservoir. So here you can see data from my colleague again, Sandra Bjørnstottir, published in 2017, and she looked at the chemical composition or the evolution of the chemical composition of the reservoir fluids, also from samples collected in our first monitoring borehole. And the first graphs basically shows you magnesium concentration in millimoles per liter, in dark gray the measured concentration, and in open triangles you can see the magnesium that we would expect if we have just pure mixing. And you can see when the measured concentration of calcium magnesium is larger than the expected concentration, like here, as you can see here, then basically we have a net dissolution of host rock minerals. So basically we get magnesium from the silicate minerals that dissolve. And that's, basically from the basaltic rocks. And, if the concentration, the measured one is basically smaller than the expected one, then we obviously have precipitation of mineral phases in the reservoir. And that is, nicely shown by her data on these plots, for magnesium and for calcium. So with this, we basically could show that, permanent storage and CO2 mineralization in basaltic rocks works. And it results in permanent storage of CO2 emissions. But then we were also interested in kind of, okay, can we see, this new carbonation? Can we see carbonation happening in the subsurface? So we drilled a borehole and cored, the section in the storage reservoir, and the borehole was drilled basically between the injection borehole and the monitoring borehole, the first one, and we retrieved a cores to look at the cores. And here you can see, that the reservoir, there are different basaltic rocks, there are different parts. We have parts that are very permeable, with a lot of vesicles. We have parts that are really kind of dense, low permeability. And this core, also helped kind of study reservoir parameters, which, was then my interest. So we were really interested in, okay, what are the reservoir parameters in these rocks? What are, the effective porosities? What are the effective surface areas? Because these are key parameters to then characterize what is kind of the capacity of these basaltic rocks to store CO2. So on the course, we did a study, using clinical computed tomography and microcomputed tomography. We did, experiments with colleagues at Stanford University, micro-positron emission tomography, and really to find out what is the total and effective porosity and the total effective surface area, which is used, to predict fluid transport and reactivity in the subsurface. And here, if it works, you can see from, does not really work. So I will go forward, but here, you basically see with a CT scan, you can then, through image analysis, you can basically get, kind of, you can extract the porosity, the pore space, which are basically the vesicles here. So shown in red, we just subtracted all the other rock parts that are not, basically a pore space. So here in red, you can see the pore space, the total porosity, which was in this example, and we did many other examples, was around 15%. And then you can also use this image analysis to calculate the surface area of the pores, which are critical, for the water-rock interaction. Similarly, then, the total porosity is not really the key parameter, it's the connective porosity. So through further image analysis, we could basically then extract, here shown in blue, the pores that are connected to each other and come up, with a connected or effective porosity, in this case of roughly, 8.7%. And, these are really powerful tools for reservoir characterization. But then, we were interested to run some core flooding experiments and see basically, okay, how is the fluid moving through these rocks, and how much surface area is that fluid seeing? Because that's, a critical parameter too. And here you can see two results, of two different cores. It's results from the micro-positron emission tomography to basically, find out the connective porosity in the effective surface area. And these experiments were run at Stanford at Sally Benson's laboratory. So here you can see one example that basically shows that the scanning occurred, with a radioactive tracer. And while the fluid was injected, this radioactive tracer was injected, the CT scan was done, and what you call the positron, micro-positron emission tomography was conducted, and what you can see is where the fluid basically flows. This radioactive traces, where do they flow in this core? Here you can see that they are basically along a linear a feature, which is a fracture in these rocks, and here you can see that the vesicles are way more connected, and that's how that tracer basically was transported through this part of the through this core. Then we basically did then a stochastic vesicle percolation simulation, how the percolation occurred in these rocks, and you can see here the effective porosity versus the total porosity. And it basically shows, if we have in red all the simulations, if we have no microporosity, and the other ones include a 1 grid cell or 2 grid cell microporosity. And here you can see that in this TDM image, what I mean with microporosity. We basically found out that the vesicle itself, is obviously forming the major pore space, but the vesicles also, have microporosity around them. And this is basically, illustrated here. We have very fine crack networks around each vesicle, and that provides basically a microporosity. And that's simulated here, how, the effective porosity versus total porosity looks like if we have, if we include this microporosity in our simulations. And then, we basically came up with, used experimental in our simulation results and other experimental results, illustrated here in black, to basically show, okay, what kind of effective porosity do we really need in order to have, efficient and high capacity for CO2 mineralization in these rocks. And, these experiments are all, published by Hellisheidi and co-authors in 2018. But you can see here, these are basically, our core flooding experiments of Stanford. But what the graph shows you, if you have no microporosity, you have very, if you have a total porosity of 15%, you have basically very little effective porosity. So in order, if we have micro porosity, this cracks around the vesicles, we need a minimum total porosity of 15% to have, any kind of a higher effective porosity that is, ideal for the CO2 storage capacity we would like to have in these rocks. Obviously, if we are honest, we need kind of a basaltic storage reservoir needs a total porosity above 15%. to have, a high enough effective porosity to store fluids. So, this is kind of the physical storage characterization or storage reservoir characterization part, and work is going on in that. But what we also looked at in the core is, do we have any mineralization, or did any carbonation, precipitation of carbonate minerals occur? And in here, in this case, in these vesicles, we had new growth of carbonates happening, as illustrated on this picture. We then also, we realized during the injection that our monitoring borehole had, a submersible pump installed, but this pump failed after a certain time. And basically it failed because it was encrusted with carbonate minerals when we took it apart. The carbonate minerals, in that monitoring borehole, basically it was mainly calcite, as illustrated here, on that XRD scan or figure. But it also had, when we measured the radiocarbon concentration of this carbonate, it had basically our radiocarbon in it. So the radiocarbon concentration of these newly grown calcite minerals, the carbon had our radiocarbon signature, so we know it precipitated from our injected CO2. So these was basically, very promising results. We could prove for the first time fast CO2 mineralization in a geologic basaltic reservoir in the subsurface. And then, my colleagues at Reykjavik Energy took that further and, developed a CarbFix II project, which is basically now an industrial application. What they do in Iceland now, they inject 10,000 tons of CO2 per year and 5,000 tons of H2S into the geothermal reservoir, not in the shallow reservoir we used. So they move to a deep reservoir. They inject these emissions 24/7, 365 days. That they stored quite a lot of CO2. They could also show, and you can go on their website, they can basically prove that CO2 is mineralized and that the H2S emissions are also mineralized. So from our initial results, they developed basically an industrial application, and that's now a very successful application, and it saves a lot of money and abatement cost, mainly for H2S emissions for that power plant. So colleagues also then did kind of a calculation, with that dissolved CO2 injection we developed and the mineralization, how much does that cost per ton of CO2? You can see here that, the cost they calculated in terms of capture, transport, injection, monitoring. Obviously, the capture costs, as always, are, the most expensive part. But roughly, the CarbFix and Reykjavik Energy scheme for CO2 storage sequestration is basically $25 per ton of CO2, which is really good and competitive on the market of CO2 storage. So that is really, really good news. So the key message is basically, from our CarbFix I pilot project, we successfully demonstrated permanent disposal of CO2 as carbonate minerals in situ and basaltic rocks. And we did that, for the first time. More than 95% of the CO2 has been mineralized within less than 2 years. But what we also could show that kind of, our applied tracer technique was very successful in monitoring, the fate of the injected CO2, and it was a quantitative monitoring. So we could basically do an accounting of how much CO2 was mineralized, and we could also then show that a target storage reservoir formation in basaltic rock needs at least, a 15% total porosity and enough, connectivity between the pore space to sustain, long-term injection. What we don't know right now, still open question is, the longevity of such a storage reservoir is an open question. We don't know, and hopefully somebody will address that in the future. And obviously, there is a trade-off between porosity and reactive surface area. We need reactive surface area to, for this rock-water reactions happening and for the mineralization happening. But if the porosity is too big, then we obviously lose effective surface area, because there is a higher overlap of the pore space. So there is a trade-off between these two parameters, and we have kind of find the sweet spot in any basaltic reservoirs. And then lastly, CarbFix II demonstrated the economic feasibility and industrial application of this newly developed CO2 and H2S disposal technology. But that said, these are all, really good news and exciting research. Obviously, it has a global significance. If you look at it, if you look, basaltic rocks are the most common rock type on Earth. Here you can see a global map with, kind of in orange, the ocean-rich basalts. And here in Iceland, we obviously, used a reservoir basically is on an oceanic ridge, the mid-Atlantic ridge. But there are also continental basalts like the Columbia River basalt here, the Camp basalt in the southeast of the United States, the Deccan Trap, the Siberian Trap. So, on every continent you have basaltic rock formation. So as my colleagues calculated, these are theoretical calculations, there is enough storage capacity in basaltic rocks. If it's feasible or not, that has to be tested with additional, a pilot scale study. But it's promising, we could store a lot of CO2 in basaltic rocks. But to end, my presentation, basically we need a reality check always at the end. Yes, we have, the reservoir capacity for a significant storage of a lot of CO2, in the billion-ton scale. But, what does that really mean? So I like, to use that example from Martin Blunt at Imperial College. And so if we take 6 billion or 6 gigaton of CO2 per year, that's 20% of the current global or of the global CO2 emissions from fossil fuel burning. So just 20% of that. And we calculate kind of the volume of that CO2 at reservoir conditions. And we compare that volume to, the global oil production illustrated here, which is, roughly 8 million barrels, which translates to 1.5 times 10 to the 7 cubic meter of oil per day. And we compare that to the 2.7 times 10 to the 7 cubic meters of CO2 per day. So what you can see here is basically the size of, any carbon capture and storage industry. For just 20% of our emissions from burning fossil fuels is basically the size of the current oil industry. So if we want to go down this route, we have to build basically that capacity. And, we need the workforce to, to basically do that job. So this is kind of a reality check, where we stand, because right now, there are not that many active CO2 storage happening, especially in Europe. So I would like to acknowledge again, this study, CarbFix I study was not possible without obviously funding. Funding was provided, by the US Department of Energy, by the European Commission through different grants, the Nordic Fund and the Global Climate Energy Project. And so I would like to acknowledge them. And now, I'm very happy to answer questions. Thank you very much.
Thank you, Juerg. It was a fantastic talk. Thank you for the intro to mineral carbonation, update on CarbFix and the reality check, which is always very important. We do have quite a lot of questions, and if anyone would like to ask a question to Juerg in person, you are welcome to do it now. If not, we will read the questions from the list. So please feel free to ask questions now.
Maybe if Andrew Moffat wants to kick us off. Andrew's there and wants to unmute. Yeah, go for it.
Yes, I was just wondering that in the conversion of the silicate minerals into the carbonate-rich rock, I would assume there must be an expansion in volume of the new lithology. I was just wondering how that's accommodated in the subsurface.
Yes, that's an excellent question, and a lot of research is going on in that field. So yes, that there is a volume expansion happening from a denser calcium magnesium silicate mineral to a less dense carbonate mineral. That expansion has to be accommodated in the subsurface. So depending on how tight these rocks are, you can imagine what can happen if that has to be accommodated in the subsurface, and especially not in basaltic rocks, because you can find quite permeable and high porosity basaltic reservoirs, but in mantle peridotite, and that's where a lot of that research is going on. This leads to cracking, or can lead to cracking. So you would form new cracks because it produces a stress on the rock, and that stress is released through, or most likely be released through cracking, and new porosity is formed. So yes, that's a critical question in more tight reservoirs.
Okay, thank you.
James Craig.
Hi, can you hear me?
Yes.
Yeah.
It's a related question. At CarbFix, intuitively, you would think that if you get magnesium carbonate minerals precipitating within the reservoir, there will be a fall off in permeability. My question is that observed? And if it is observed, what happens to the injection pressure?
Yes, so in CarbFix I, 170 or in total 230 tons of CO2 is nothing. So we have not observed any decrease in the permeability or in the injectivity in CarbFix I. In CarbFix II, I cannot really speak to that, but I know from my colleagues that over the now 4 years of injection, 10,000 tons of CO2, they have not seen a drop in the injectivity or in the production in any borehole, at that in that storage reservoir. But it's a it's a very critical question. It goes to what is the overall storage capacity of such a reservoir, and somebody has to answer that question. How it's tricky. There are obviously numerical simulations, but so far there is no actual data showing that the injectivity is decreasing, which you would expect, because there is a there is a certain storage capacity, but it has not been reached, and the reservoirs have not been stressed, right now to that point. So we don't know.
Sorry to just sort of cut in again. In the future, if as we all hope, these sort of storage options develop, there is a question about carbon accountability here, because somebody somewhere is going to have to be confident that you can not just estimate, but be confident of the amount of carbon stored in the formations. This is going to happen with conventional CCS. It's going to be true of other forms of carbon sequestration, be it direct into basalt, weathering, peridotite, whatever. Just a sort of thought.
Yeah, excellent thought, and coming, from the monitoring verification world, one part is of my research is, to develop such tools. and accounting is absolutely important. And basically, we need that accounting, we need that certification in the future. Is it, conventional CO2 storage? Right now, it's done every 5 years. For example, in the North Sea, in the Statoil reservoir, they shoot a seismic and say, okay, that's where the CO2 is, and that's how much CO2 is stored. Similarly, in reactive reservoirs, we really need the counting of how much CO2 is stored, dissolved, or in terms of minerals. And that is also true in any other method. If it's enhanced weathering, that the counting has to happen. And right now, it's happening on a certain level, but certainly not, not every CO2 molecule that is stored is accounted for. So yes, huge development has to happen, and this certification, is absolutely required, because that's where the money is involved now, because you get paid to store that CO2, so you have to certify that it's really stored.
Absolutely, thank you very much. Glenn Burke, apologies, we missed your question there. If you would like to unmute and ask yourself. Glenn is still here, thank you. I think so. I'm happy to ask it on your behalf if you prefer. I can just find it, sorry. At CarbFix, what were the typical dimensions or the diameter for the injection and monitoring boreholes?
Oh yeah, that's a good question. I hope I can recall that correctly. I mean, and otherwise it's somewhere in the papers. But I think we had an injection borehole of 8-inch diameter. Similarly, 6 or 8 inch was the monitoring borehole. And the injection borehole obviously had these two pipes going down, so the CO2 pipe as well as the water pipe that injected the water to a certain depth. And then the monitoring borehole, the first one, had a permanent submersible pump installed and was permanently pumped. And the pumped water, I mean, we sampled that, but the other part, wastewater, was re-injected into the flank of the geothermal reservoir in a other injection borehole. So yeah, it's roughly I think around 8-inch were the diameters of the boreholes.
Quite significant then. Yeah. So Kate Brody, if you're willing and able.
Hi, I think my question's actually been answered already on the chat. I asked about if you've attempted to observe these reactions in laboratory experiments.
Yes, we see the mineralization reactions, we see that in laboratory experiments. Yes, that was done basically before the pilot. We see, the dissolution, obviously the dissolution of these magnesium silicate rocks, the dissolution rates, the kinetics were studied, as well as, the minerals, the carbonation. Their lab data exist. It's just, the surprise was, based on the lab data, the surprise was how fast the reactions were in the actual field inspection project. And if you compare kind of the two rates, the field was kind of faster than the laboratory experiment. So that's usually, obviously there is a difference, that's common, makes common sense. But the field rate, was quite fast and not expected to be that fast.
Yes, they're quite impressive microstructures from those ones. Quite surprised how rapidly those reactions have occurred.
Yes.
Thank you.
Great, thank you. We have Brian Martin next, if he's around.
Hello, can you hear me?
Yes.
Yeah. Yes, I was wondering about sheeted dikes in Iceland. I presume you have a lot of vertical sheeted dikes there. And would these affect your model at all? Because all your photographs seem to be of vesiculated lavas, permeable, relatively permeable vesiculated lavas.
Yeah, no, the reservoir, we were basically, the reservoir we used was kind of a young, basaltic flow from coal from the tertiary. So it was vesicular basaltic flows. Obviously sections, as you can see in the core, was kind of really dense, more hyaloclastic type rocks. The reservoir they use now, is the geothermal reservoir at, 2 kilometers depth. And that's a purely fractured reservoir. So it's dominated by fractures and fracture flow. I cannot speak more about that, but certainly, we were not in the parts where we had a kind of the dikes. We were in a lava, quite recent lava field.
Okay, thanks very much.
Thank you. And I think Vincenzo has a final question, if Vincenzo is still with us.
Hi, yes. I would like to know how far the monitoring boreholes were from the injector well.
Yeah, so that first monitoring borehole, I showed all the data from that first monitoring borehole at depth. The monitoring borehole is inclined, as you can see, could see in one of my schematic figures. So it's inclined, but at reservoir depth, at storage reservoir depth, the distance between the injector and the monitoring borehole was 125 meters.
Yeah, I see.
And
just that was one of my curiosity to see if there was any possible other way where the CO2 could come back to the surface, if there were any monitoring well much farther than the injector well.
Yes, so we had, further away, we had monitoring boreholes, several, and we thought, we sampled then on a regular basis, and we could never see, within these 4 years of project, we could never see the traces arriving there or the CO2 arriving there. The hydraulic gradient is very, very, a low gradient, a shallow one. So it's not a steep gradient. So the natural groundwater flow is very, very slow. Too slow. That's why we did a forced gradient test to just force our injected fluid towards our monitoring borehole. But CO2. What we have to understand, we did a dissolved CO2 injection. The advantage of that dissolved CO2 injection is that the PCO2, the partial pressure of the dissolved CO2 in that injection fluid, was lower than the hydrostatic pressure. So CO2 cannot bubble, exsolve and bubble back to the surface. And that's, a key part, that your PCO2 has to be lower than the total hydrostatic. And it stays dissolved in the reservoir. It can't exsolve and come back. And then, it gets neutralized further away from the injection borehole. And that even lowers further, the partial pressure of the dissolved CO2. And so leakage, is actually not a big part, or potential leakage is very, very low because of that, dissolved CO2 injection.
Okay, thanks a lot.
Yeah.
Okay, looks like that was our last question. Thank you very much again for all the questions and all the great answers, and a really fascinating talk, Juerg. Before we close up, just one last announcement. Our next AMG OGT will be on the 25th of March, and it will be presented by Professor Eva Hartai from Miskolc University in Hungary on the production of energy and metals in an interlinked process, how ultra-deep metal enrichment can be utilized. Please join us. This will be advertised via our normal routes. Stay tuned. Thank you very much. Many thanks, Juerg, again.